Okay, so here now we'll start discussing about fatigue of composites. We introduced fatigue. We discussed about this. We discussed about the methods that have been introduced the last 200 years. And now we'll talk about fatigue of composites and come back to this little guy asking now why fatigue is important for composites, in addition to the importance that it has for metallic or concrete or whatever other structures. And fatigue is important for composites for several reasons, more than the reasons that we have to be worried for other materials. And I have here a list. It's a longer list than this, but I have a list that makes fatigue critical for composite structural components or structures. First one is the reason that composites nowadays are used for critical structural components. It was not the case years ago. Years ago, we were using composites only for secondary elements, but now we have composites in a lot of applications as critical components, so main structural components. And they are obliged to receive all these fatigue loads, and they have to survive for several millions of cycles. So this makes their performance fatigue sensitive, and that's why we need to understand fatigue of composites. When we go then for structural applications like bridges, I have here a comparison of a concrete bridge over a composite bridge, for example. And for concrete bridges, fatigue is not really an issue, and it's not fatigue sensitive because it's so heavy that the fatigue load, which is the life load, is more or less, or you can call it insignificant compared to the dead load of a bridge. So the weight of a bridge is so high that the loads of the traffic are very low. However, when we talk about lightweight composite bridges, these live loads are becoming very, very significant. And there is why we have to discuss about fatigue in composites. Fatigue also is important for composites because they are brittle and behave linearly up to failure. And this makes their failure to be sudden without a lot of notice before. We'll see also later on strength degradation criteria or measurements about strength degradation. We can see that composite materials retain their strength until to failure. And then we have this kind of sudden death phenomenon that we call it there. So the material fails without any identifying any damage. And that's why we should be able to predict this by assuming or understanding fatigue behavior. You remember also we saw this physical testing, the fatigue design verification. And to do this, as we discussed before, is too much expensive and costly in time. You need long time to do this testing, and you have to spend a lot of budget, a lot of money for this. So the ability to simulate the fatigue behavior is very significant, especially if you can reiterate fatigue design, so reiterate design concepts to estimate or to end up with a structure that is able to assume, to sustain the loading that is needed for the entire lifetime. And of course, discussing about structures that operate in several applications, they're operating outside, so durability is significant. Durability, it's not only the performance in long periods, but also the performance under different environmental conditions. So there, we need to discuss about fatigue and durability of composites to justify or to secure that these materials can be used for several engineering applications that work in in the open air, as we call it. So these are reasons, and there are other reasons that I'm not mentioning here that make fatigue of composites, materials, and structures very significant. So we'll talk about a bit of history of fatigue of composites now, repeating more or less what we did for metallic structure, but now focusing on composites. And I'm coming back to this to show the significance of fatigue of composites. Starting from this publication from Hulbert in 1955, where he wrote that fatigue and creep are such important aspects of dynamic and static behavior that among the wealth of data accumulated around reinforced plastic materials, it is astonishing to find little or nothing published about their property. So in 1955, this is 70 years ago, we didn't have a lot on fatigue of composites. If you see today, we have more than 30,000 cycles. I'm passing with fatigue. We have more than 30,000 articles related to fatigue of composites. And this shows the huge interest of the researchers in the field. These articles discuss the effects of the R ratio, frequency, so the loading on the fatigue of composites. They are investigating viscoelastic behavior of the materials. They investigate the influence of the constituents of the fiber architecture, so the way that we create the materials. They talk about the differences between the loading patterns. If we are in tension or in compression, the fatigue behavior is much different. And then they're also investigating modeling techniques like SN curves or constant life diagrams, similar to Goodman diagrams, to assume or to introduce techniques that are more appropriate and more applicable for composites compared to what we have already for metallic structure, which is mainly the structures that have received mostly the investigations about fatigue. So the first studies for fatigue of composites are coming with their introduction already as structural components back in the 1950s. We have in 1942, we had this report from the United States discussing about properties of plastics. Yeah? Composites at that time were mentioned as plastics. Huh? And then in 1948, we have this document again from US Aeronautics Advisory Committee discussing about the mechanical properties of laminated plastics. And there, at that time, they were discussing, in between others, glass fiber laminates. Huh? And they found that, between others, glass fiber laminates had the best performance regarding fatigue. In 1957, we have other publications talking about fatigue properties of fibrous glass reinforced materials from Boller. And then we have more or less 20 years to see that there is not any agreement about design data. So remember, in 1950, we have a lot of experimental investigations. And in 1970s, we know that already we have so many data, but we don't know how to use this data. And this is what comes from the publication of Harris in 1977. And this introduces the main issue that we still have today. We have a lot of data, and we are doing investigations for specific material systems with specific objectives for a specific application. Usually this investigation is done locally, and there is no connection between similar investigations somewhere else, and there is no common understanding of the results, and there is no common agreement about the methods that have to be used to achieve a complete and accurate fatigue life modeling and prediction. So these are topics that are circulated along the years. 1977, we've seen also discussions like this later on and later on until today, that we are still in the same more or less situation, of course, with much more knowledge than what we had before. This is the discussion that we already did, that composite materials were introduced as fatigue insensitive, although we know today that they are not. So composites are used in a lot of applications, not only in aerospace. We've seen the first laser boats in the 1940s with the glass fibers introduced by Owens in the United States. And we've seen a lot of different applications. Today we have winterbind rotor blades that are facing more than 100 million fatigue cycles during their lifetime. 100 million is 10 to the power of 8. And a lot of applications that are facing intensive fatigue loading during their lifetime, and they need to be considered during the design. We are in this period of time where composites are used massively. You see this green part here, are used massively in several engineering applications, and especially there are some applications that wouldn't be able to be manufactured or designed without composites, like winterbind rotor blades. Without composites, we will be still in the windmills of the 1900 period, where we could only produce locally very few quantities of energy to feed the specific needs of small industries or house equipment. But now we have these huge blades, and these huge blades can only be made by composite materials. So this is exactly what I'm discussing now and where we are. A lot of structures are facing significant loads, fatigue loads during their lifetime. Aircrafts, around 2-3 million cycles. Bridges, more than 10 million cycles. Helicopters, reaching 100 million cycles, and this is exceeded by winterbind blades in their 25 years of operational lifetime. And these are composite structures. And these composite structures should be able to sustain these loads. And the methodology or the way that we do it today is by unfortunately adding quite significant safety factors, which means that we are over-designing these structures, which means that they are not functioning properly, and they are more expensive. So, as Raman mentioned before, we know today that composites or fatigue of composites is more troublesome than fatigue of metals. We see self-heating. What is self-heating? Is the temperature that is introduced in the material by the friction during fatigue loading. And this self-heating imposes doing testing at lower frequencies. And this means that we need more time to do a fatigue testing of a composite material compared to fatigue testing of metals. In metals, you can go up to 25 hertz of frequency, and you can complete 1 million of fatigue cycles in less than half a day. And for composites, we cannot go more than 10 hertz, which means that we need more than a day to complete 1 million of cycles. Composites then, depending on the laminate configuration, so reorientation of fibers, which means that fibers that are oriented in a specific orientation, when we load, imagine plus minus 45 degrees fibers, when you load, these fibers tend to follow the load orientation, which means that the material properties are changing during the loading, and are changing for two reasons. Are changing because of this reorientation, so the material actually becomes stiffer, but at the same time we have damage in the material which makes the material weaker. So we have two competing phenomena that have to be considered during the loading and during any kind of methodology that we have for fatigue life prediction to give accurate results. We don't see this effect in metallic materials, for example. And we know also that composites are strain rate sensitive, and especially those materials that are more susceptible to viscoelastic effects. So those materials that are more ductile show sensitivity to strain rate. And this is important for composite because the loading rate is changing their properties, actually, is related to the properties of the material. And if you remember what we were discussing about the loading types, we had the case where we had a variable amplitude loading with overshoots. And these overshoots actually are assumed to be in the same frequency. So the overshoot means that you have a faster loading of a material for a specific cycle. And there we should assume that for this cycle we have different properties, which is of course not easy to do when we do modeling. In composites also we have manufacturing defects. We've seen before when we did this X-ray videos, we've seen voids in the adhesives. These voids are actually parts of crack initiations. They are damage in the material and can be considered as points of initiation of damage that can lead to failure. We have also misalignment of fibers. You remember this discussion that we said about the anisotropy of composite materials. The fiber alignment is very significant depending on the. Here I can start a short diagram again. I can plot here the material property, either stress or stiffness, with the angle of the fiber orientation. So imagine that you have a lamina with fibers in this direction, and we have a lamina with fibers at the off-axis direction. So if we plot, if we do a test, a tensile test, in both cases, and we plot the stress, the strength, or the stiffness of the material with the angle, we can see behavior like this. So here is normalized, 1 to 0. Or we can see behavior like that. This behavior, the first one, is related to what we call a highly anisotropic material. And this can be carbon fibers, for example, at the 0 degrees, like this one. This is a less anisotropic material. It is anisotropic, but the difference between the strength at 0 degrees or the strength are 90 degrees, if you want here 90 degrees. So when the material is in this configuration, is not so much different. So imagine when we have a highly anisotropic material for a misalignment of fibers. During fabrication, you might align the fibers at 5 degrees instead of 0. This slight misalignment of fibers can lead to more than 50% loss of the stiffness. And this is what we mention here, the misalignment of fibers that can be due to manufacturing defects, can significantly affect the material performance. And this should be also taken into account during the design of a composite structure. That is not an issue when we talk about metallic materials. The other point that is significant is the preconditioning, or if you like, the exposure of the material to different environmental conditions or different serviceability conditions, like solvents or whatever during service. So composite materials, we know that they are very sensitive because they can absorb water. They are sensitive to temperature. They have usually the polymers that we are using, they have low glass transition temperature. So they become, they go from the glassy state to the rubber state at low temperatures, which means that at operational conditions, when they operate at the open air, they might they might face transitions between different stages of the material. And of course, we know that the testing that we do for identifying the material properties is very sensitive to a lot of parameters. We'll see tomorrow. We'll see a lot of cases like that where we have the effect of the tab failures. We have the effect of the gripping of the material. We have the effect of the alignment of the material on the testing devices. And of course, there are standards for investigating the material properties. But we've seen today that even these standards should be interpreted, if you like, in a very careful way. We should not follow the standards without criticizing and trying to really understand what the standards recommend. So today also we know about composites that we have identified all the damage modes. Already since the 1970s, we had kind of understanding about the damage modes of composites. We know that composites fail due to matrix cracking, actually, that is happening in the matrix. Then interface failures that separate actually the matrix from the fibers. This damage is growing, and it is translated, if you like, to the lamination, so separation between the layers. And then finally we have for materials that are fiber dominated, so materials that are having fibers along along the loading direction, we can also see at the end a fiber failure. So these conditions, if you like, or these damage modes have been already identified by very early, 1970s more or less. And this diagram shows exactly this difference between composites and metals, and shows actually the complexity of composites damage and failure compared to the complexity in metals. And this again brings back this discussion brought on the table by Raman before, that the investigation of composites behavior is much more challenging. Only if we see this list here, we know that for metals, what is important is the crack length, and we actually talk about one crack in metals, whereas in composites we have several cracks. We have broken fibers, we have delamination, we have matrix cracking, we have composite cracking, we have debonding, we have voids, we have so many effects that are actually synergized. They work together to lead finally to the fracture at a certain point. So we know now that it's more troublesome to test composites. And we know now that composites are not fatigue insensitive. What has been introduced in the 1970s is not, we know that is no valid anymore. Composites fail, and they fail in a kind of controlled way. We can fit this behavior by using similar equations. This is from between the two lines, we have a power curve. It's a Basquin curve, actually. The rest is a curve coming from another model that we'll discuss in a couple of days. We know that there is no fatigue threshold for composites. So there we cannot see, mainly we don't see this kind of threshold, but the curve is asymptotic to the axis of the number of cycles. We know that the S-N curve of composites can follow actually this power law equation, and it has 3 different slopes that can be assigned to damage mechanisms. In the initial stage, we have mainly matrix cracks, and when we go to different loads at lower stresses, we have mainly fiber failures that we'll see also in the experimental data that we'll show in tomorrow, actually. And we know also that composites are failing with stiffness degradation during the lifetime following specific trends, like more or less the trend that is followed by all composite materials is similar to what we saw in this schematic diagram. There is a significant drop in the beginning. At around this stage 1 can take 10 to 15% of the lifetime. We have a stage 2, which is more or less with a constant slope. That is the most of the lifetime of the material is showing an evolution of stiffness in this stage. And then we have a sudden stage at the end that might be 5-10% maximum, where we have the drop and actually the failure of the material. So this trend is followed by any composite materials that we've seen, except some specific cases that we will discuss again tomorrow, where we have kind of increase instead of decrease for certain stages. And there, just remember what we said before. In some cases, we have competing mechanisms. We have the mechanism that is shown by this diagram, where we have the damage accumulation to the material that leads to the stiffness degradation. But in some cases, we have mechanisms that increase the stiffness, like the reorientation that we've seen before. So when you have material that have fibers that are oriented with the load, this means that the stiffness is increasing. And then at the end, the behavior that we see here is a synthesis of these 2 mechanisms, or of the effect of these 2 mechanisms. So we know also that composites, first of all, follow, as we discussed already, follow a Weibull distribution. So static strength, fatigue strength, number of cycles, they are not normally distributed. They are actually log normal distribution, or if you like, they also fall into the category of Weibull distribution. And there is an introduced model, actually in 1975, by Han and Kim, that is also known as the SLERA model. You see here with highlighted the SLERA model, which is the strength, life, equal rank assumption. And this model simply says that a specimen that ranks in a certain position at static strength probability distribution, it should be at the same rank in fatigue life distribution. Simply saying this means that a specimen that is strong in static strength or static loading should be strong also in fatigue. Of course, this cannot be validated. If we test a specimen, we break a specimen in static loading, we cannot break the same specimen in fatigue. But we've seen that more or less this is correct. And this SLERA approach is somehow shown schematically in this diagram, showing that the same distribution of the static strength, which is here, can be transferred to the distribution of the fatigue strength in terms of loading, or of the lifetime, which is related to the number of cycles to failure. So we said before, we know that composites follow a viable distribution. These are publications of our group that investigated these effects and show these results. This is a viable distribution with data. The different colors correspond to different loading levels of in a fatigue SN curve. And we see that these are data that are well dispersed in a viable distribution cumulative probability plot for different materials, actually, different types of specimen types. We know that for composites, we need to test at low temperatures. Actually, what we know for composite materials is that the increase of temperature is beneficial. You see this plot, it's a schematic plot. The frequency on the horizontal axis and the number of cycles on the vertical axis. And we've seen with experimental evidence that the increase of frequency helps to increase the fatigue life as long as we do not have self-generated temperature. So this is what we call the self-heating. Because when we start having self-heating, this self-heating makes the material softer, and this is damaging to the material. So we have a kind of decrease then of frequency after a certain point, depending, of course, this frequency of transition depends a lot on the material and the loading type. The reason that makes the increase of frequency helping the material to achieve more cycles is exactly the reason that we've seen here. We reduce the time under load, and time under load for a material means creep. And creep for composite materials is a viscoelastic phenomenon that at a certain level can also cause damage to the material. And this means that when we reduce the creep, we can increase the fatigue life. This is what is called in the investigations creep-fatigue interaction or creep-fatigue coupling. We know also about composites that we can investigate them by different methods. We can investigate their performance. What we see here is a work that we did 5 years ago, more or less, to monitor the damage in glass fiber composite laminates by different methods. One is the photography. The gray photos that you see here are typical photography. And the color photos are the photos from the infrared camera. Actually, the color photos show the temperature on the material. And what we see the first rank here, the first line, a specimen tested at a high stress level, 68 megapascal of cyclic stress. And the lower photos correspond to 47 megapascal, so to a low stress level. And we investigated the damage. Damage is shown in the material by the darker areas. And we've seen that we can actually monitor the damage by taking photographs. And we can correlate this very well by the increase of temperature. You see here that the material is more damaged. We have temperature increase, and the temperature here reached or exceeded 50 degrees. The TG of this material was 60 degrees, which means that we were approaching the glass transition temperature of the material. The same happened at lower stress levels, although the damage was not so evident because the damage in lower stress levels were more distributed along the specimen. But again, we could see that at a certain level, so you see here it's around 98% of the lifetime, so approaching the total lifetime of the material, we have some stress, some strain concentration, so some damage, which is shown by this darkening of the material, and this corresponded to increased friction. You know, friction is increasing when we have damage. It means that we have more more roughness, so the friction with the fatigue loading is higher. That's why we have these effects. So here we've shown that it is possible to monitor the damage evolution on the material by using optical methods like those presented here. We know also that the materials, composite materials, have so a viscoelastic behavior, and this is correct. This is true also for viscoelastic for thermosets that are not assumed that are not viscoelastic materials. We've seen this recovery effect. You remember this Forrest Gump discussion that was sleeping and then was recovering. So what we did here in 5 years ago, more or less 6 years ago, we tested the composite laminates. Actually, it's this same investigation, the PhD thesis of this guy there. So we tested composite laminates, and in this case, we tested for a certain number of cycles, so 20% of the lifetime at this stress level, and then we were letting the material to recover for 2 hours, and then testing again, and then recovering again, and then going like that until the material fails. And what we observed is that the material managed to increase the lifetime by a lot. We'll discuss tomorrow about this. When we are interrupting the loading, so the black curve here is the curve corresponding to the interrupted loading, the red curve corresponding to the continuous loading. So we see that this interruption helps the material to recover and actually increases the fatigue life of the material by a certain amount. We've seen also the other way around, again, the effect of the viscoelastic behavior of the material by doing the same test, but now instead of letting the material to recover, we were creeping the material. We were keeping the material at the highest, so the sigma max, the maximum cyclic stress, for certain lifetime. And there we've seen, of course, we were continuing this up to the end. And we've seen also here that we had a significant effect of this viscoelastic phenomenon, this creep phenomenon, on the material behavior. So the continuous line, the continuous fatigue is the black line. The curvature, the line corresponding to, coming back here, the line corresponding to loading with creep for 2 hours is the blue one, and the line corresponding to creep for 48 hours is the red one. And what we've seen here is that the short creep is beneficial for the material, especially at high stress levels, while the longer creep times were leading the material to fail earlier. And this, again, the effect that short creep can be beneficial because it relieves the crack propagation, but longer creep times can create damage to the material due to this creep itself. So we know also about composites that the Goodman diagram is not good anymore. The Goodman diagram, you remember, it was a linear interpolation between the amplitude and the mean stress. Now we know that for composites we have a more what we mentioned there, the Gerber line diagram. It is explained in this publication years ago. The main parameters of the CLD that we are introducing nomenclature here are the 3 sectors of the CLD, which is the sector related to the compression loading, only compression. The sector here, where we call the TT, the tension loading. And there is a sector here, which is tension compression mixed. And it is compression dominated where we are on the left side and tension dominated when we are on the right side. These diagrams are plotted on the sigma m, so mean stress over sigma amplitude plane. And we use actually here the SN curves are these radial lines. This radial line. So any point on this line corresponds to a specific S-N curve. In this case, is the S-N curve for R equal to 0. This is the reversed S-N curve, and this is the S-N curve for infinite. Infinite means from 0 to a kind of negative. We will discuss again in details about these constant life diagrams, but what we should keep here is that Goodman diagram is not anymore valid for composites. So the other point that we've seen that is related to the usefulness of Goodman is that for composites, we have different behavior in tension and compression. We know already that composite materials are better in tension than in compression because of buckling that happens when we have compressive loads. And in fatigue, we have the same phenomena. And we know that constant life diagrams are shifted either to the right or to the left, depending on the material that is investigated. And this again devalidates, if you like, the usefulness of the Goodman diagram. This has been initially presented by, again, a work from the group of Harris back in the 1990s. It was in, yes, 1988 in this case. So the CLD, as we said, depends on the material. There are materials that are better in compression, others that are better in tension, and there are materials that are obeying, if you like, to different types of constant life diagrams. But what we know and what is justified here by this slide is that Goodman, which is this first approach, more or less, is not
तेरा डेट ऑफ बर्थ क्या 89
there is a background noise. Someone has to mute.
Please mute your microphone. Hello.
Okay, thank you. Okay, thank you.
Hello. Mr. Harpreet Kaur, can you mute your mic, please? Yes, please.
All good?
Yes, you can continue.
Okay, thank you. So in these diagrams, we have regions that correspond that we have more fatigue loading and regions that we have more creep loading. So you can imagine when we approach loads, I can plot, probably it will be easier to explain. We have a loading type. And this is load from 0 to a certain value of stress. This case that I draw here with my very poor drawing skills corresponds to R equals to 0. Because I'm going from 0 stress to a certain level. So you remember R equals minimum over maximum. R equals to 0. This is this case here. And this is a purely fatigue case because we are not keeping the material at a certain value. We are keeping the material at a, this is a combined fatigue and creep phase. I will explain. Because we keep the material, we go to 0. So we let the material relax. If we have a loading that is going like this, for example, a new loading that is like that. It has a very small amplitude, but it has a very high mean stress. This means that we are here, very small amplitude, very high mean stress, so the SN curve is like that. This can be R equal to 0.9, for example. And the maximum or the worst case in this scenario is this curve, which is R equals to 1. And there is the curve that corresponds to pure creep. This is a curve corresponding to pure creep. So this is what we saw here, that the constant life diagrams give also an information regarding the component, the creep component that we have on the material. When we go to lower stress ratios, stress ratio of 0, of 0.1, 0.5, these stress ratios are related more to fatigue loading. When we approach the sigma m axis, we are more discussing about creep. We are discussing creep effects. Then we know also about composites that are related, or their performance is related to the multi-axiality, so to the stress components. We can have, I go here and then come back. You know this is mechanics. It's not related to fatigue only. But when we have on-axis loading along the fibers, then we have uniaxial stress states. If we load the composite material, so an anisotropic material in general, off-axis, then the stress state that we have in the material is already a multi-axial stress state. So coming back here, we have always a plane stress condition, because also we assume that material are thin wall structures. Composite structures are thin wall structures. So we have a plane stress everywhere. And what we have realized 20 years ago, we realized that the effect of the transverse normal stress, so the sigma 2, and the shear stress on the fatigue life of the composite structure is very, very significant, even if these stresses are very low compared to the normal stress, to the sigma 1, to the principal normal stress. And this happens because of exactly the anisotropy of the material. Even if these stresses are very low, we know also that the strength of the material along these orientations or these directions is very low. And what we realized at this time, it was actually this is part of my PhD 25 years ago. We realized that the design codes at the time were neglecting some of these stress components and assuming the failure only related to sigma 1, to the principal stress. And we attributed at that time the failure of specific components. In this time, we were investigating wind turbine rotor blades. We correlated this failure exactly to the design by neglecting the transverse normal and the shear stress in the fatigue loading. So multi-axial stress is important, and it should be considered in design. We also know that specimen types and size play a role. There are works. This is a work from the group of Bronsted that investigated this, and they showed that there is an effect of the specimen because of the stress concentrations at the loading conditions, at the loading boundaries, and also the stress concentrations during the transition between the loading boundaries and the material and the region where the material fails. And we've seen also this with adhesive specimens, where we followed in the work that we published. Actually, it's a work for 2025, very fresh, and the previous work in 2 years ago. That when following the ASTM recommendations for adhesive specimens, ASTM says that we can use either of these three specimen types to test in quasi-static and fatigue. What we've seen that if we use these three specimen types, we have different behavior. Actually, the smallest specimen showed better results in all the cases. So this is coming to back up what I said before about the standards and how blindly, if you like, we should follow the recommendations and not question every time what we read from the standards. So, composite materials give the potential, if you like, or the freedom for new geometries and new joints. So we know now that we have to address the phenomenon of fatigue differently because we have different materials, we have different joints, we have different types of connections and different geometries. And this is what is visualized here when we have a very thick adhesive joint. That was not the case when we were investigating metals, for example, with very little joining techniques, so with bolts, for example, or when we were investigating typical aerospace joints that assume that there is only a very small, a very thin adhesive layer or a very thin film adhesive connecting two components. In the case of thick joints, which is part of the investigations that we are doing last 4 or 5 years, we see that the adhesive itself plays a very significant role for a lot of reasons, and some of the reasons are related to the structure of the adhesive itself. We've seen a lot of voids in the material. We've seen the crack length deviating from the midplane, and all these are components that have been overlooked in the past, not necessarily because people didn't care about this, but because they were not involved in the failure, in the fatigue failure of other types of structural components. So now with these new materials that we are investigating and introducing in structures, we are opening also new ways for research in this case. We've seen that this, with all the methods that we have now with fractography and all these X-ray methods, we can identify the structure of the materials. We can see the fracture propagation, and the question here is to introduce methods or to adapt the methods, if you like, for example, fracture mechanics methods, to consider these effects and consider this type of geometries that are not usual and are not known or used before when these methods were applied. We've seen that the fracture mechanics methods can be used at certain states and at a certain range of materials, and they can be applied to model behavior of new, if you like, structures. Here we have a joint with a 2 millimeter adhesive layer as a connection between the two adherents, and we managed to plot you remember we discussed before about the Paris plots, the FCG curves. So we've seen that Paris plot can be useful here, but also we introduced an additional parameters to do a total fatigue life modeling, and that's why this is a bit more. If you remember, the Paris law is this. The Paris law equation that we've seen before is this part, and here we introduced one element and the second element to consider the low. So this is the threshold value, and to also consider the maximum. So this is the G critical, the behavior of the material at this maximum loading conditions. So these are the small adaptations that we've said that can be used for analyzing composites by using the methods that are already known in the literature. So we did testing in different modes. And then by using this testing, you can develop failure criteria that we'll see in Wednesday and Thursday to model and predict actually the behavior, as we see here, of joints that are using the same materials as those that are investigated in the fracture mechanics joints and are failing in similar ways. So there, by using this type of methodologies for fatigue life prediction, we can actually predict the lifetime of a composite material, in this case, the lifetime of a joint, at specific fracture mechanics or fracture loading. So what is expected from these methods is to end up with what we have here, fatigue lifetime prediction for new and existing structures. Because if we develop methods for fatigue life prediction, then we can either design structures with credibility that can sustain specific loads for a certain loading time, or, which is also very, very significant and important, to come and assess existing structures to be able to give recommendations if this structure still has some lifetime that can be used for more, so extend the lifetime of the structure, or if this structure has already, if you like, consumed the lifetime that was attributed and should be somehow replaced. And with this, I think I concluded for today. We've seen that fatigue is an issue. It's a big problem for engineering structures. Composites are more troublesome. It's very complicated to identify how composites fail, and actually it's more complicated. It's quite easy to understand how they fail because we can now visualize all the damage that is created, but it's complicated to correlate this failure to appropriate methodologies to be able to predict the lifetime. Prediction capacity is limited, and it is also hindered by the missing experimental data that are available. There are not a lot of experimental data available to validate theoretical models. So this is where we are, and probably this is where we are going. I think now everybody is tired, is fatigued. So I will stop here. Thank you for your attention today. And if you have any questions for now,